Okay, let's dive right into this explainer and unpack how quantum computing veteran D-Wave is attempting to solve, well, the industry's absolute biggest headache. If you track the quantum race, you already know the stakes are incredibly high, and the engineering hurdles, even higher. Today, we're looking at a completely fascinating new development published in Nature this August 2026. It details how a company totally synonymous with one specific type of quantum computing is making a massive, massive play for another.
So the crucial point we always come back to is that current quantum computers just make way too many errors to be practically useful at scale. Qubits are insanely fragile, right? They lose their state if you look at them wrong, if the temperature fluctuates even a tiny bit, or sometimes literally for no apparent reason at all. This wild error rate is the great bottleneck of the quantum age. Every single company out there is scrambling to figure out how to correct these errors. Which brings us directly to D-Wave's highly specific and honestly very clever new strategy.
Section 1. D-Wave enters the race, a shift in strategy. To really understand their new approach, we first need to look at D-Wave's somewhat unusual history here. Founded way back in the last century, D-Wave is basically a legacy player in a brand new field. They didn't start out with general-purpose gate-based computers like IBM or Google did. Instead, they built quantum annealers, massive machines specifically designed to solve a huge class of complex optimization problems. But recently, they've completely shifted gears. They are stepping right into the general-purpose gate-based arena, and they're bringing a very specific technological bet along with them.
And this specific technological bet is exactly what makes their pivot so interesting. They've opted for a dual-rail qubit, also known as a fluxonium qubit. To fast-track this whole thing, they actually went out and acquired a startup called Quantum Circuits, which was a spin-out from Yale University that specializes in this exact architecture. It is a bold move, pivoting away from their traditional annealers into a specialized gate-based technology that promises a really unique advantage when things inevitably go wrong.
Section 2. The dual-rail qubit. How it works.
So how exactly does this build a working qubit? Well, imagine two linked resonators. Kind of think of them like microscopic left and right buckets. The system works by physically placing a single photon right into this environment. If you were to measure it, that photon is always going to be in either the left resonator or the right one. But because this is quantum mechanics we're talking about, you can actually place that single photon into a superposition of both left and right simultaneously. That fragile little superposition is your qubit. It's simple, it's elegant, and it's mechanically very distinct from what others are doing.
Section 3. A smarter correction. Tackling errors.
Now, this specific left and right architecture introduces a completely brilliant concept, the error hierarchy. Look, in most quantum computers, errors are just messy. They're unpredictable and super hard to pin down. But in a dual-rail qubit, the absolute most common error is simply the photon escaping the hardware entirely. It just leaves. This is called an erasure, and it happens to be 5 times more common than anything else. The second most common error is a phase flip, and bit flips, they are practically non-existent. We're talking occurring at a rate of 10 to the negative 6. The real beauty here isn't that errors magically don't happen. It's that the system's failures become highly predictable.
Because it's just incredibly easy for the hardware to detect a missing photon. I mean, you literally just check if the box is empty. You don't need a massive array of extra qubits constantly running these complex diagnostic codes just to figure out if a mistake happened. D-Wave is betting that because their primary error so loudly announces itself as a simple erasure, they can use far simpler, much more compact error correction codes. And what does that mean? It means they can achieve useful logical qubits with significantly less physical hardware than their competitors. It's a total efficiency play.
Section 4. Proving it works. Validating the concept.
Now, putting two individual qubits together usually completely messes up that delicate error hierarchy we just talked about. But D-Wave just published a major milestone paper in Nature showing they actually successfully entangled 2 dual-rail qubits. They pulled this off using a tunable coupler, positioned right between them. To make them interact, they simply turn the coupler connection on, so one qubit partially occupies it, wait just a fraction of a moment, and then shut it right back off. This direct interaction is the absolute foundation of actually performing real calculations rather than just passively holding data in memory.
And the speed of this operation is just staggering. 500 nanoseconds. That entire entanglement operation takes just 500 nanoseconds from start to finish, with the actual wait portion taking a mere 200 nanoseconds. As D-Wave rightly points out, you wouldn't even have time to check your watch. This essentially proves these operations are fast enough for practical, real-world quantum computing.
The critical takeaway here, as D-Wave's Trevor Lanting confirms, is that this lightning-fast entanglement doesn't ruin the magic. Usually, creating two qubit gates completely distorts the error profile and introduces all sorts of messy new problems. But their data explicitly shows that even during these high-speed entanglements, photon loss remains right about 0.5% per entanglement, making it still 5 times more common than anything else, while bit flips essentially just stay at 0. The hierarchy totally survives the computation.
It's also really fascinating to know how this direct entanglement approach heavily contrasts with some of the other major players in the space. Take Amazon, for instance. Amazon also uses dual-rail qubits in their research, but they rely on an intervening transmon qubit to act as a sort of middleman to mediate connections. Amazon never directly entangles their dual-rail qubits. D-Wave's Nature paper entirely validates that you can in fact connect them directly, beautifully simplifying the physical architecture.
Section 5. The Road to 2028. Future Milestones.
Of course, while the Nature paper completely proves the core concept, as they try to scale this up, massive engineering mountains start to emerge. Currently, as the number of gates increases, they're seeing an unexpected quadratic decrease in fidelity and state purity. They suspect this is largely due to drift in calibration parameters. Furthermore, they still need to figure out exactly how to detect those missing photons mid-calculation, not just at the very end of the run. And finally, managing a system where error types are so wildly different requires a massive amount of classical computing power just to interpret the error data, which is known as the syndrome.
But D-Wave has a very clear, aggressive roadmap. With the entanglement validated here in August 2026, their immediate near-future goal is perfecting that mid-circuit erasure detection. If they can nail that down, they are aiming to scale up the hardware to 181 dual-rail qubits by the year 2028. And that 181 number? It's highly significant because it provides a large enough sandbox to rigorously test forms of the surface code error detection scheme, which is the exact stepping stone they need to reach hundreds of logical qubits.
Which leaves us with the ultimate question. While intense calibration and scaling challenges absolutely remain, for sure, we have to ask, will building a system where errors naturally and loudly announce themselves be the ultimate solution that finally wins the quantum race? D-Wave is literally betting their entire future on it, proving that sometimes, the best way to deal with a mistake isn't to try and prevent it entirely, but to make sure it's just impossible to ignore. Thanks for joining me on this explainer, and definitely keep your eyes on 2028.